Okay, so we're going to finish this part. We were talking about uh, primary frequency regulation, and we discussed the droop control characteristic, and we were here talking about the steam turbines. And this is a general description of what a steam turbine is. And there are two types. One type is the tandem compound. I'm not sure if I am pronouncing this correctly. Tandem. So this is just one shaft. All the turbines are going to be connected to the same shaft, and also the rotor of the generator will be connected to the same shaft, as you can see in this figure. So we will have a high pressure turbine, an intermediate pressure turbine, a low pressure turbine, all connected to the shaft of the rotor of that generator. In this configuration, we're going to have three types of main dynamics. One has to do with the steam chest. We will have a boiler that will produce steam at high pressure, high temperature, and that steam is going to be sent to the steam chest. So here we're going to have the dynamics of the steam moving inside the steam chest, and that's going to be one main dynamic. We are going to have a valve that will control the flow of steam. And we can have some dynamics associated with the valve as well. But when the steam passes here, it will go through the high pressure turbine, and we're going to assume that the turbine is represented by an algebraic relationship. So the dynamics involved with that are going to be assumed that are infinitely fast. After this high pressure steam turbine, you will get some power. That energy in the steam, some of that will be converted into torque that will be sent to the shaft. But some of that energy will leave the turbine, will not be able to convert all that into torque, and that steam will be reheated. So that steam will pass through a reheater, and here we're going to have the second main type of dynamic in the description. After the reheater, we're going to have an intermediate valve that will control the flow that will go to the intermediate pressure turbine. And again, instantaneously, some of that energy will be converted into torque and sent to the shaft, but the rest of the steam that will still have some temperature and pressure will be sent to a crossover. So we will have some dynamics related to the crossover. All the pipelines that will take the steam to different low pressure turbines will be considered. So this is the third main dynamics we will consider, the crossover. And finally, this is sent to the final low pressure turbines. In this figure, you have 4 low pressure turbines that will finally convert that energy into torque that will be sent to the shaft. The steam that leaves these low pressure turbines will be sent to the condenser. We will get water that will be sent to the boiler to produce steam, and the system will be closed. Yeah. So that's one type of steam turbine. The other type is the cross compound, and the cross compound will have 2 different shafts, as you can see in the figure. So in this case, you will have a high pressure and intermediate pressure connected to the same shaft. So you will have one generator rotating at higher speed. You will have a reheater. You have the steam chest and the valve here, and after the reheater. But after the intermediate pressure turbine, you will send this to the crossover, but you will have low pressure turbines connected to a different shaft, and this will be connected to a different generator. So this is another type, another configuration for these steam turbines. We will stick with that. Yeah, this is the one that we're going to study. And for this, we can come up with different models, and if you use commercial software, you will find a large library with different description of turbines. But in this course, we're going to just use one, which is going to be the standard model from IEEE. Yeah? So that's the model we will use. This is a general purpose turbine model. It can fit very well the description of the steam turbine, tandem compound. But also, if you tweak the parameters, you can also describe a hydro turbine, with some approximation, of course. Hydro turbines are more complex, more nonlinear, and even though this model can give you some description, we will always have some errors. But this will fit very well that steam turbine we describe with the tandem compound. The description of this is given as a block diagram. In the block diagram, here we are assuming that the variables that are in the block diagram are in frequency domain. And you have used this in your control system courses and other courses you're doing some design at the moment. So when you see this diagram, you see frequency, but that is not the signal in time domain, but frequency domain. So in this diagram, you will have a controller. This controller will have some pieces that you should recognize from the droop characteristic. We have an error in frequency here, so we will have a reference for the frequency because these are in per unit. If we're using 60 Hertz, this frequency for the reference is going to be 1 per unit. And here we need to measure what is the frequency. If this is connected to a generator, we need to measure what is the frequency of that generator. So if there is any deviation of that frequency with respect to the reference, then we will have here an input that is different than 0. Otherwise, the input will be 0, and the only input that you will have here in the steam chest and going out is going to be given by P0, which is basically the set point for that generator, the power set point you might have. If the frequency is 1 per unit, remember that the torque and power in per unit are going to be the same. Let's look at the controller. You have 1, 0, and 2 poles. Do you recognize anything of what we have discussed so far in that first block? So we talk about the droop characteristic. So what can you say about droop characteristic if you look at that controller? Yes. But I don't know really what K or T. Okay. Well, K is going to be the gain of your controller. It will be proportional to, it will, if this K is greater than 1, will amplify the errors that you have in the input, so it will increase the output that you have in that block. But then you will have poles and zeros that are typically studied in control system. So in this case, we're going to recognize that the poles that you have in the transfer function are going to be related with eigenvalues in your system. Yeah, the eigenvalues, then we have some characteristic about the stability and how the system will behave dynamically. Well, you get the same information from the poles, which is the denominator that you have in this block in this diagram. But in a few slides, I'm going to make the connection of this with what we had been talking during the whole semester, which is the time domain representation. We haven't used these diagrams yet. Everything we have talked, everything is in time. And we talk about differential equations and algebraic equations. So what I'm going to do after we discuss this general model, we're going to derive what is the set of equations we need to describe this turbine governor. But to answer your question about what is the gain, those coefficient K1 is basically a gain. You have an input, you will multiply that input by a gain, and you get an output that is proportional. Another thing that might be useful when you look at this diagram is to see the connection that there is between the frequency variable, which is S, which is the Laplace operator, and the time variable. So if you remember from control system, if S tends to 0, that is actually the same than thinking that the system is the system behavior when the time go to infinity. And when S go to infinity, that is the same than thinking that is the behavior of the system when time tends to 0. So you get the initial condition, and also you get the steady state condition by looking at the extreme of your variable S. For example, if you look at this controller, and we don't look at anything else, we can see what is the output of this in a steady state. So what would be the output? You need to see how is going to be the transfer function when S is 0. Sending S to 0 will imply the behavior when time go to infinity in a steady state. So if S is 0, all these time constant disappear, and what do you have at the end? Just the input multiplied by K1. Okay? So what is that exactly? And we talk about the droop characteristic. What did we say about the droop characteristic?
Lower value, and that means at a lower frequency.
Yeah. Yeah. So if you have a drop in the frequency is going down because you have more equivalent load than generation. We need to increase our generation, right? And we want to determine how the power will be increased in each generator. So the drip control will give you that linear relationship, and it's going to be proportional to the frequency deviation. And that is exactly what we have here in a steady state. That's the inverse of K. So what we have for the droop characteristic, we have the frequency and we have the power from a given generator. And if this is 1, then you have an initial power, which is P0, that is the set point. We will run the power flow to initialize all the variables, assuming that the generator will produce P0. We will assume that the frequency is 1 per unit, and that is the initial equilibrium point. But if you have a disturbance that lead to a power imbalance, let's say you have more load than generation, then the frequency will drop. If we don't do anything, the system will lose stability. There will be a blackout. So if the frequency is going down, we need to stop that. And how we're going to stop? By putting more generation from the generators. So we decide to use this inverse characteristic. That's why we call it the droop characteristic. And this slope is going to be the speed regulation constant we're going to use. So basically, if you have a frequency here, F1, so you have a delta frequency that is F1 minus F0, and this is negative. What we want to have is an increase in the power from P0 to P1. So the characteristic that we got is P1 need to be equal to P0 minus 1 over RD multiplied by delta F, which is going to be F1 minus F0. That's the droop characteristic, okay? So what do we have in this controller? We have an error. That's the error of frequency. So if the frequency is changing, we will measure what is the frequency, but you will have a delta frequency here. And then that delta frequency will be multiplied by a gain that we're going to call K1. So K1 in this case is going to be the inverse of the speed regulation constant. As the frequency is negative, this, you have a negative sign there. This will give you actually the delta P that the generator need to increase their power injection to the system. So what we see in that block diagram, in a steady state, when S tends to 0, if S tends to 0, the Laplace operator, that implies that T tends to infinite. So we're in a steady state. The behavior in a steady state will come exactly from the droop characteristic we talked last time. Yeah, but the other dynamics that we have will be important because it will tell us how we're going to move from this point to this point, and we will have some dynamics to consider. Is that better? Yeah. Pues. Yeah. What do you get here? Okay. Yeah. No, it should be the same. So is that what you use? I'm sorry. Yeah, I need to review that part, I guess. Yeah. Are you positive about this? Yeah. So that's the infinite value or the steady state value that you will get. I think you're right. So the limit 1 s tend to 0 of this will give you the steady state value at the end. Yes. Yeah. So how that would be in our model then? Can we do that? Where is it? So if we apply this here, what do we get? That's strange. Yeah. Yeah, let me check this. You know, I need to check what is the theorem that we have there for the steady state value. It doesn't make sense. Okay. The transfer function should be just what you see inside the block. So yeah. So let me check that part, and I will explain that to you on today's Wednesday. Yeah. So let's leave that pending, so I don't tell you anything that is wrong. But if you look here at the transfer function, and that is exactly what we want. You know, if S is 0 in this case, then basically you're getting the steady state behavior, which is given by the droop characteristic. What do you see here, P0? What is that? Again, from the droop characteristic, that's the initial set point for the generator. That's the power that you define based on economic dispatch. How much should be the power from the generator that will minimize the cost? So here we are adding basically the droop characteristic. K1 then is going to be the inverse of the speed regulation constant. After this, what we're going to have some limit for the power. The power will have hard limits, technical limits, mechanical limits. So the power will move from a minimum and maximum value. And then that is going to be the order for the opening of the valve before the steam chest. So if we need more power, then the opening of the valve need to be larger. And then we will have the dynamics, which is first order block for the steam chest. This will define the characteristic of the steam going in through the steam chest. And then the energy of that, some of that is going to be converted into torque that will be sent directly to the shaft of your system, but the rest will be sent here to the reheater. And then you have another first order behavior for the reheater. We're going to reheat the steam, and then we will send that to the intermediate pressure turbine, and some of that will be converted into torque, and that is going to be sent to the shaft. And the final part is the dynamics in the crossover. So you have these pipelines in which you send the steam at low pressure, and you send it finally to the low pressure turbines. And that is the general description that we will have for that model. Okay. So in this course, we're not going to get too complicated with the whole description, and we're going to use, for simplification, we're going to use a reduced version of this model. What is going to be the reduced version? We're going to assume that we don't have a reheater and we don't have crossover. So basically, we have one high pressure turbine, and the main dynamics we're going to retain is going to be the one from the steam chest. So K2 is going to be 0, the same than K3. K2 and K3 will be 0. So we will just have the steam chest in that description. So that's the model that we are going to review. Okay? Any questions so far? No? So the model that we're going to study is just one high pressure turbine, no reheating, and no crossover. And we will have the controller. So this is the part that we need to discuss, and how we're going to obtain this set of differential algebraic equations. So to do this, we're going to separate the controller. You have here a second order equation for the denominator. We don't like that, so we're going to separate this in two blocks. When we do that, then we will have these two blocks now, and we can name this block and what is the purpose of each of these parameters. So K1, we know that is the droop characteristic, the slope in our control characteristic. And K1 will be the inverse of the speed regulation constant. And here you will have a first order differential relationship with a time constant T1. And this is going to be basically related to the valve behavior. We need to open a valve at the steam chest that will let the steam go out to in the direction of the turbine. So we need to consider that behavior, but that behavior is going to be a linear behavior, first order behavior. And then at the output of that block, which we have here in the controller, we're going to name that variable y1. Then y1 will be the input to the other part of this controller. Here you have a 0 and a pole. So in the 0, we're going to have a lead characteristic. Typically, this is going to be a phase compensation we will have. And the pole that you have there is going to be the lag behavior related with the governor itself. So you will have a description of the governor with a lagging behavior, but we also will put some phase compensation, and that is done through the time constant T2. So after that block, then we will have the variable y2, and that is going to be subtracted here in this sum. So you will have P0 minus Y2, and Y2 will be basically the output of this controller. We like to separate this because that will ease the obtention of differential algebraic representation for this model. On the other side, nothing changed. We're just naming here mu, which is going to be the input to the steam chest. If P0 minus Y2 is within the limit, mu will be exactly equal to that P0 minus Y2. But if for some reason these are out of the limit, either greater than P max or less than P min, we're going to set the value of mu at the limit. With that, then we will send that as an input to the steam chest, and we will determine after that first order block, we will determine what is the mechanical torque we finally obtain in this generator. Okay, any questions so far? Were you able to follow the description? Yes, Ryan.
Why? I'm just normally used to reference being the constant, but why is the reference a negative?
That's the standard description. That's the standard description. Also recognize here that you have a negative sign here. If we make this positive, we can put it in your form. So the reference minus your variable. Yeah? But that is the standard description. Most importantly, I want you to recognize that what we have here with P0 and these blocks that you see here is nothing else than the droop characteristic. If you have a frequency deviation here, F is less than the reference, then this is going to be negative. And in a steady state, then there will be a change, delta P, that will be proportional to the frequency error. And that is going to be negative because the frequency will be below the reference. But then that is multiplied by -1 here. Therefore, P0 plus some delta P is going to be the order to open the valve in the steam chest. Therefore, we can produce more torque and more power in that generator. Yeah. So I want you to see the droop characteristic here. Now, with this definition for the variables that you see in red here, we're going to obtain the set of differential algebraic equation we need. So we start with the first block. In the first block, we have the error in frequency and the droop and valve characteristics. So when you use this in frequency domain, all these relationships are algebraic. And that is the advantage of using this frequency domain, because the differential term that you have in time are going to be just algebraic representation in frequency domain. So that's why we can get this block diagram, because these are just algebraic description. So in frequency domain, if you look at this first block, you have Y1, which is the output, which is going to be this transfer function multiplied by the frequency error. And that's what we have here. So we can take the denominator here and send it to the other side of the equation. So you have S T1 multiplied by Y1 plus Y1. Basically, we have this expression. The Laplace operator is only involved with this term. So when we get the Laplace inverse to convert this in time domain, the only term that we need to consider here is going to be this one. So the inverse of this S Y1 is the derivative of Y1 in time. Yeah. What is the Laplace inverse of Y1 in this equation? It's going to be Y1, but in time. Yeah. So that's what we're doing here. So you need to remember that the Laplace transformation of derivative is nothing else than the variable in Laplace in the frequency domain multiplied by S. Yeah. So the inverse is going to be the same. So if you see a term in the frequency domain that is multiplied by S, the Laplace inverse will give you the derivative of that variable. So by taking the Laplace inverse here, you will have T1 multiplied by the derivative of Y1 in time, which is right here. The Laplace inverse of Y1 is nothing else than Y1. And the same thing on this side of the equation. K1 multiplied by that frequency error is going to be the same expression in time domain. But the frequency now is going to be changing in time, not in frequency. So with this, we can send Y1 to the other side, and finally we got the first differential equation, the mathematical description for this first block. First part of the job is done. Now we move to the next block, the lead lag behavior that we have.
So the time constant T1, does that just somehow relate to how long it takes for that?
Is the time constant of that first order dynamic behavior. Yeah. So that's when you see this, that is exactly what it is. T1 in that form is going to be the time constant of that first order behavior. Yeah. So in this model, we will see different time constant. This has to do with the phase compensation, which is part of the control, and also the lag of the governor. And this is something physical. It's related to the design of the steam turbine. So what is the characteristic of the steam chest that will give you what is the time constant T4? So this is the first step. The second step, now we have how much is Y1, which is going to be obtained by solving the differential equation. Now that's going to be the input to this second block. And with that, we need to obtain Y2. But this is different from before, because now you have a 0 and a pole. So in frequency domain, Y2 is going to be the transfer function multiplied by Y1. So you have this description. And these, to make it simple, we can make the following trick. We can keep the pole here, but we're going to define Y1 divided by this denominator. We're going to define it as a state variable in this model. So we're going to define, as you can see here, as Y3. This block is going to be Y3. So if this is Y3, what you have for Y2 is nothing else than T2 is Y3 plus Y3, all in frequency domain. So we have an equation. If we know Y3, this is how much Y2 will be. For Y3, which is defined here, we can proceed in the same fashion as we did it before. So we are going to send the denominator to the left side of this equation, and we get T3 is Y3. So this is going to be a derivative term plus Y3 equal to Y1. Now, we have two equations for this block. One is for Y2 and another for Y3. In time domain, this one, we already did it in the previous page. This is going to be the derivative of the state variable Y3. So basically here you have T3, the derivative of Y3, equal to negative Y3 plus Y1. So in the second block, we obtain a second differential equation related to the dynamics of this block. And for the other equation, which is Y2 equal to this in terms of Y3, we're going to have here Y2 is equal to T2 multiplied by the derivative of Y3 in time plus Y3, this equation. And even though that sounds tricky, we already have an expression for the derivative of Y3 in time. So what we're going to do here in this expression, we're going to replace immediately what is the derivative of Y3 in time. So the derivative of Y3 in time is going to be negative Y3 plus Y1 divided by T3. That's, you get it from there. So if we pick that expression and replace it here, you're going to have this expression for Y2. We reorder terms here. Y2 is going to be Y1 multiplied by this ratio of the time constant T2, T3 plus 1 minus T2, T3 for Y3. So as you can see here, because we have a 0 and a pole for that lead lag behavior, we're going to get, in this case, one differential equation and one algebraic equation. So that's different to what we got before. For the last part, that's very simple again. we need to get the input, mu. But the input mu will depend on what is the value for P0 minus Y2. So if P0 minus Y2 is greater than P max, then we're going to set that value to the maximum. If this is smaller than P min, we're going to set that value to the minimum. Otherwise, we're going to make mu equal to P0 minus Y2. So mu will be exactly what we're going to determine based on the droop characteristic. And finally, with that mu, whatever value of mu we get, we're going to get the last description, which is a first order block. And in frequency domain, this is Tm is going to be this transfer function multiplied by mu. So we repeat the process. We pick the denominator, send it to the left side of the equation, and you get T4 multiplied by Stm plus Tm equal to mu. In time domain, we get the Laplace inverse here, and we will get T4 multiplied by the derivative of Tm in time equal to negative Tm plus mu. And the description of mu in time domain will be exactly the same than what we have in frequency domain. So bottom line of this, we're going to get, for this simplified model, we're going to get 3 differential equations, one for each block. And for the lead leg, we're going to have an additional equation, which is going to be algebraic. For the last block also, we are going to have a variable mu, which is algebraic, that is going to be defined in this fashion. So we need to monitor where P0 minus Y2 fall, because then mu might take any of these 3 values. To sum up, the model that we will have for this simplified model for the steam turbine and governor is going to be given by these 3 differential equations, 1 algebraic equation, and this definition of the variable mu that can take 3 values depending on the value that we obtain for P0 minus Y2. Okay, so in this exercise, I have shown you how we are going to convert these block diagrams into a set of differential algebraic equations. Everything we have worked in this course is based on a set of differential algebraic equations. That was the starting point. We did all the analysis in that formulation. So what we're going to do here, if you have a model with the description that we have studied so far, we need to add these to our set of differential algebraic representation for your whole grid. So if you have 3 generators with turbines and governors, then you need to add this set of equations for each one of them. Okay, and that's the last part of this. Because of time, we're not going to spend time working how we're going to implement this in our code. That's an exercise you can do and see if you can get the simulation, and you can work out with the code we developed to run a time domain simulation. But for the sake of time, we're going to use the code that I developed in the grad course that I taught before to my PhD students, and that is in Canvas. So we're going to use that for this part, and actually for any system you want to simulate. That is a general code, so you can simulate a system with any numbers of generators and any topology for the grid. So the example is this one. We study a system that is similar to this. We study the oscillation problem. Basically, we have a system with 4 buses, and we have a generator with 6 seconds of inertia on the left side, top left. On the top right, we have another generator with 3 seconds of inertia. And here at the bottom in our system, the one that we used before for oscillation, we assume that we have an infinite bus. Now, because we're controlling frequency, we're not going to make that assumption anymore, and we're going to consider a finite generator at this bus. There is no infinite bus anymore because we have frequency control in this system. So this generator still will have a large inertia, and this is the standard version of this system. We call it the 9-bus system, and we will simulate what happened for this system. The data for this system is already in Canvas, in the code that I uploaded to Canvas. So new data that we have, because we will have the 2-axis model for all the generators. We have the grid model, of course, and now we are adding the governor. Another thing that the code has, but we're not going to study that part, we are going to assume that that is working, which is the voltage controller. Each one of these generators will have a voltage controller that will regulate the terminal voltage to keep it as close as possible to a reference that each of the generators will have. But if we look at the governor and turbines, these are the parameters that we're going to consider for this simulation. David asked for the time constant. What is the mean of the time constant? And here you have some data. So this is the time constant of the steam chest. So it's a very low time constant. So the behavior for the steam chest should be pretty fast. The behavior for the valve in the steam chest is a little bit slower. And then you have a behavior for the governor, and also a behavior for the phase compensation. These are the blocks that we have right here. Yeah. Okay, the last part has to do with the K1, which is the inverse of the speed regulation constant. K1 in this case, for all generators, we're using the same parameters. So K1 will lead to a speed regulation constant of 3.3%. So what is the mean of 3.3% based on our discussion? From 0 to nominal, to 1 per unit in the, yes. So that's the definition. In this case, in this system, the generators are injecting some power. So the frequency deviation will not be as large. Otherwise, we will hit the limit of the generators. Okay, so that's the data. You have the code. You can try to repeat this simulation, but here I am showing you some behavior. So in this case, we will have this behavior for the speed. What can you tell me? So we have 3 machines, and that's the behavior. What can you say about it? This is new. We studied oscillation before, but this is a different type of dynamic behavior. This is pretty close. I think that if we simulate to 30 seconds, we should be able to reach a steady state for this system, but we can verify that. I think we're very close here. But one thing is that there is an increase in the load. If we don't have this frequency controller, then the system will go into a blackout. We will not be able to satisfy the demand. But because we have this droop characteristic, we have a governor for each of the machine, then the power injected from each of the generator is increased to balance that load. When we reach that perfect balance, right here, when the frequency finally is stabilized, right? What else can you say? So we have one characteristic, which is the stabilization of the frequency. What else do you see? Pretty quick, yeah. What do you think? Why do we have that behavior? Okay, Okay, the increase in the load happened instantaneously. We're assuming that at time 0 here, there is an increase of 100 megawatts, and that happened instantaneously. Where did that power come from? Because the generator will not be able to change the power output they have, because we have a turbine with some time constant. It will not change instantaneously from the inertia. So that part is going to show almost a linear decay in the frequency, because we're taking that deficit in power from the kinetic energy stored in the rotating mass. What else do you see here? You have 3 generators, but what is the behavior of the 3 generators? They kind of go together, right? But, as you said, David, this is not a problem purely related to the frequency regulation, but we also have oscillation in the dynamic response. This increase in 100 megawatt will excite also the modes, the oscillation modes in the system, and you can see that there are some oscillations. What machine do you think might oscillate more? That's the system. Generator 1 has a large inertia. Generator 3 has the least inertia. Probably that's one that might oscillate more with the frequency excursion. And that should be it. It's hard to see with this color, but it's the clear green color, which is the one that we observe there. Okay. To be precise, when we study this type of behavior, if you see that a response, this is typical of a system with a slow mechanical response. We might see this on the western interconnection. Eastern interconnection might be faster. So in the lab of Dr. Gilles Liu, she has a real measurement of the frequency in the system. And you can see different disturbance in those systems. But you will be able to realize that this type of behavior are more frequent in the western interconnection. So that's a characteristic of a slow response for the system. When you have this, then one of the things that we're going to pay attention is how much is going to be the maximum deviation in the frequency. That is called the frequency nadir. In this case, we have a 0.02 per unit. So a drop in 2%, right? Which can be very large in a realistic system. But that is a very good measurement that we can have for this type of behavior. What is the problem of having a large frequency deviation, a large frequency nadir? Is that troublesome? Why? We might trigger load shedding in the system, and that is undesirable because that will involve with some negative economical consequence. Very quickly, the other description that we're going to see exactly what David was talking about, that there is a linear drop in the frequency at the beginning. And we can describe that with the rate of change of frequency, the slope, basically. So that's another characteristic. A system with very large inertia, maybe this ROCOF is not going to be that significant. If you have more inertia, the slope is going to be smaller in that case, which is attractive, will give you more time to control the frequency. So that part right there typically is known as the inertial response, because basically we're balancing the load in the system using the kinetic energy from the rotating masses. The governor have not responded yet because this is involved with mechanical components that will take more time to develop, slow in front of a steep immediate change in the power. So that's going to be the inertial response. But after a while, and you can see here that that linear behavior is broken here, and the frequencies start like being increased a little bit. And that is when we have the governor response. So after a while, in this case, maybe after about 2 seconds, maybe, we can see the action of the governor, and the governor is able to stop this frequency decay and push the frequency even higher a little bit until the frequency is stabilized. During that process, this is the mechanical torque that we have in the generators. And as you can see, from the initial value to the final value, look at the 3 curves. The increase is about the same. Why the increase in the torque is about the same in the 3 machines? All the same. And that's the assumption that we consider for this system, which is about 3.3% the speed regulation cost. So what we're going to do now, and this is the description that we're going to have on Wednesday, we're going to run some simulation, and we're going to see what is the impact of important factors. What could be an important factors here to study? We want to get some feeling about what could be the behavior of the system if we change some parameters in the system. One can be the speed regulation constant. What about if the machine have different speed regulation constant? How this might be different? Because one of these generators might be a coal power plant and might have a slower response, and maybe we need to use a speed regulation constant that is different. What about the inertia? That's another parameter. So on Wednesday, we will play with that simulation and try different parameters to try to get a better understanding of how they might impact the dynamic performance of the system. Yeah. And also, we're going to talk about the question from Kelly. So we need to review this part, and I'm not going to lie to you. So let's check it, and we're going to discuss this on Wednesday. Yeah? All right. Any question? Any question? Yeah. I will see you on Wednesday.